Vonk will talk about resurgence, transseries, nonperturbative.
Thank you. Well, you've had...
I hope you'll tell us what those words
Yeah. At least you've had plenty of time to soak up the words in the title. So I want to tell you about some ideas and results that are quite old, actually, already in the mathematical literature, but that have recently become more popular again in the physics literature, and that have led to some nice results. And this is sort of the motto behind all of this. What do you do when perturbation theory is not enough? So the plan for what I want to tell you is the following, and I want to take a very pedestrian approach today. I want to spend most of my time on a very simple toy model example, just because it really quite nicely shows what's going on here. So I want to start off by some motivation, then discuss this toy model example, then give you a glimpse of these techniques called resurgence, and then end with some applications and modern results. And as you will see, many of the words that I use here actually appeared yesterday in the first talk of the conference by Marco Gualtieri. And the techniques I'll be using here are actually the ones he called slightly old-fashioned. So I won't have too much to say about that, other than that it would be very interesting to see what can be done by his modifications of these techniques to these problems. So let's start by a little motivation. So in physics, physics is not mathematics. In physics, often we cannot treat problems exactly. We get a problem and we just cannot solve it exactly. But what we can usually do... Oh, this looks very ugly. Let me see if this is a generic. Yeah. Can I use the PDF instead of the PowerPoint, just to make sure that the formulas... Yeah. But I have a PDF here as well, I think. Did you put it on here? The other one, the top one. It's showing here, so I can show you the laptop maybe. No. There we go. Perfect. Thank you. Let's see if this still works. Yeah, great. That looks like a formula. Okay. Sorry about that. So to continue, in physics we often have problems that we cannot solve exactly, but we can only solve exactly in some limit. And then we want to find some small parameter x that we can perturb in, so that the solutions we find are actually perturbative series in this parameter x. Now this approach might have two types of issues. The first issue is that the expansion that you find in this way might be an asymptotic expansion. So it might have zero radius of convergence, which is of course a problem if you want to calculate actual numbers. And the second problem is the well-known fact that some functions don't even have a perturbative expansion. They have a vanishing perturbative expansion. And as we will see, and as is quite well known, these two issues are actually quite closely related. And this is the general idea of the mathematical theory that's called resurgence. So what I will try to explain to you today is that often in the coefficients of an asymptotic series, there's a lot of information already about nonperturbative contributions to the associated function that you want to calculate. And as a result of this, we can often learn about physical nonperturbative effects, so think of instantons, solitons, D-branes and string theory, from purely mathematically studying the perturbative solution of our problem. So, like I said, let's think of all this in a very simple toy model example. And to show you how simple the things are that I want to show you, this is an integral we all know and love, the Gaussian integral. And all I want to do in this toy model is perturb this a little bit by a quartic term here. A quartic term here. And you can see that if I take this lambda here very small, if I take it 0, of course I get back my Gaussian integral. And if I take it very small, then I expect something that's pretty close to the original result. So I expect this problem to have a good perturbative solution. And you can actually quite easily perturbatively solve this problem. You can split off this exponential part of the quartic term. You can expand that in a power series to get this. And then you can say, well, if I now exchange this sum and this integral, and of course if you're a mathematician then you get a bit scared when you do that, but let's be physicists for the moment and just do this. Then you can say, well, what I have left is simply moments of the Gaussian integral, and we can calculate those. Now, like I said, you might not like this exchange of sums and integrals, but you can solve this problem in different ways. You can find a differential equation that this result satisfies, for example, and then construct a perturbative solution of this differential equation, and you will get exactly the same result. So these moments, you can calculate them, and you find some answer that is indeed a power series in lambda. Well, and then you might say, okay, I've solved my problem. I found a power series solution in lambda. But maybe this is not really quite the solution you are looking for. And the reason for this is that if you look at these coefficients here, they grow quite fast with n. Actually, if you use a Stirling approximation, then you can see that they grow like 16n to the power n. And that means that if I multiply these coefficients by this lambda to the power n, then this whole term grows like 16n lambda to the power n. And no matter what lambda I take, at some point this is going to be a number larger than 1. So at some point, the terms here are going to grow and grow and grow. So this sum diverges for any lambda. It's an asymptotic series. It's not a convergent result. So you need a way, if you're a physicist and you want to calculate numbers, you need a way to turn this formal series back into a function. And the standard trick to apply there is that of Borel resummation. So let me remind you quickly of what this is. So we have an asymptotic expansion, and let me first, to be really clear, remind you of what an asymptotic expansion really is. So an asymptotic expansion is a power series of this form, such that the partial sums approach f when x goes to 0 along a certain direction in the complex plane. And I really want to stress that this is something very different from a Taylor series. So if I have a Taylor series, what do? Well, I fix some number x, and I just start calculating terms here, and I go higher and higher and higher in order, and I get a better and better and better approximation. This is not the case for an asymptotic expansion, as we just saw. So there you have to do the opposite thing. You first fix some big n here as an upper bound for your sum. Then you get some approximation, and then you send x to 0, and your approximation gets better and better and better. So it goes sort of the other way around. And an important point here is that to send x to 0, if x is a complex variable, I have to tell you how to send x to 0, because I can do this along different directions in the complex plane. So an asymptotic expansion really is related, as opposed to a Taylor expansion, to a direction in the complex plane. And this, of course, leads to the well-known Stokes phenomenon. A given function may actually have different asymptotic expansions depending on what direction in the plane I choose. And a famous example of this is the Airy function, for which it's known that if I go from positive x or from negative x, I get different asymptotic expansions for this function. The other way around is, of course, also true. If I will apply this trick of Borel resummation, then I also have to tell you first what direction I'm working in. So Borel resummation will be a trick to construct a function that has a given asymptotic expansion in a given direction. So how does this work? For those of you who don't really remember this from their undergraduate mathematics courses, you have an asymptotic series, and the FGs grow too fast for it to be a convergent asymptotic series. So they grow at least like g factorial. And let's now consider the case that they grow exactly as g factorial. Then you can do this very naive thing and just divide all the coefficients by g factorial to get a new series, which is the Borel transform of the series. And this expansion will usually have a finite radius of convergence. And now if we assume that this not only has a finite radius of convergence, but can actually be analytically continued, hopefully to the full complex plane, but at least to a line to infinity, then we can do the following. We can go back by using this Laplace transform. So we take this Borel transform of the series, we plug it into this Laplace transform, and then if you do some algebraic manipulations, you will see that you'll get exactly your original series back. So the Laplace transform is actually an inverse of this Borel transform. And you can show that indeed this works and that the function you find in this way, because this is really a function, I give you a number x and I can calculate this just as a number, that this function really has the required asymptotic expansion given by the original fg series along this direction, x equals r times e to the minus I theta. So just to show you that this works, these are some ugly formulas, but I just wanted to show you that this can actually be done. So this was our quartic integral asymptotic expansion. And you can calculate its Borel transform. That's very easy. You just divide by an extra n factorial. So the n factorial here becomes an n factorial squared here. And you can actually calculate this sum. You can spend half an afternoon on doing that, or you can just plug it into Mathematica, and miraculously it gives you the result. And the result turns out to be essentially some elliptic integral. It's an elliptic integral where the argument is a slightly complicated function of s, and there's some complicated factor in front, but the result is still relatively simple. So you get a result for this Borel transform. And it's defined basically everywhere in the complex plane up to some poles. For example, when s equals minus 1 over 16, you have some problems. So this can be done, and then you can also do the inverse Borel transform and get a function out of this. Now, of course, this might lead to a problem, because remember, we needed to have direction to do this inverse Borel transform. We needed to do this Laplace transform along a certain direction in the complex plane. And as I said before, this guy has a pole when s equals minus 1 over 16. So in this case, where lambda s equals minus 1 over 16, so where s is minus 1 over 16 lambda. So if I decide to do my Borel transform in the negative real direction, it's more, yeah, sorry, it's a quarter root branch point, really. Yeah. But that's singularity. That's the important part. I cannot integrate over it. So I have to choose either integrate above or integrate below. And this gives me two different answers. So I get two different functions corresponding to my original function. You might ask, what's the difference between those two? Well, it's quite easy to find, because if I integrate like this or if I integrate like that, then the difference is, of course, the integral around this thing. The pole is at minus 1 over 16 lambda. And you see from this that the result from integrating around this pole will be something of the order e to the minus 1 over 16 lambda. So I get a difference, but I also see that this difference is now a non-perturbative function in lambda. Right? It has a minus 1 over 16 lambda in the exponent. So if I try to Taylor expand this, I'll get all zeros. So this is a very general lesson that we have to pick up from this. So we've seen, this is a bit of a summary from what we've done so far before we go on to the more physical examples. We have seen that the Stokes phenomenon tells you that a single function can have different asymptotic expansions. We've also seen that the Borel resummation takes a single asymptotic expansion, but can lead to different functions by different Borel resummations. Now, there is still usually a one-to-one correspondence between functions on the one side and expansions on the other side, but you need to choose a direction for this. Once you've chosen a direction, then this map is one-to-one. But if I now start changing this direction, then these jumps may occur. And this jump on the one side is called Stokes phenomenon. This jump on the other side is what I just shown you, that this Borel resummation slightly changes. And this change is actually by a non-perturbative expression, physically often an instanton. So one more thing I want to explain to you before I go on to the general theory is why do we think of this as an instanton? Well, let's look back at our original integral. What we really did, so remember I just took the exponent of this guy, expanded that, plugged it into the formula. So what I really did was a saddle point approximation there. A saddle point approximation around the saddle x equals 0. But of course this quartic polynomial has two more saddle points at x equals plus or minus I over 2 square root of lambda. And you might as well saddle point approximate around those points. And you can do that as well. And you see that if you take this quartic polynomial and you start now writing it as an expansion around x0, well, this takes a bit of work, but you will see that it has to form 16 over lambda plus quadratic terms and higher in x minus x0 squared. And this 16 over lambda is exactly the 16 over lambda that we found before. So you really, when you would expand around this other saddle point, you would find an e to the minus 16 over lambda. You would exactly find the contribution that we now found as the difference between the two.
You mean 1 over 16 lambda? Right.
Yes, you're exactly right. Sorry. Yeah, 1 over 16 lambda. Yeah. So you would find exactly the difference that we found between the two Borel resummations. And that's why we think of these jumps as instantons. They are really sort of related to other saddle points in the integral. So two things to note, I already more or less mentioned them. These contributions are invisible in a perturbative lambda expansion. So they're really non-perturbative contributions. And if you follow the numerology a bit, then you might have seen that this number 16 appeared on two places. First of all, we had this Stirling approximation to these coefficients that had a 16 in there. And then we found this, well, let's say instanton action, 1 over 16, which also has this 16 in there. Now this is not pure numerology. If I would have had a different number a here, then I would have found the same different number a here and there. So you can show that indeed this number 16 in the end comes from the number 16 in the beginning. In other words, in the purely perturbative expansion of my result, I already have a number which tells me something about the non-perturbative answer. So the perturbative series already contains information about non-perturbative results. So the whole upshot from this, and the thing we want to generalize to more physical problems, is that there's a relation between the perturbative series and the one instanton result. And it's something like, if I take one Borel summation of my perturbative result, and I take another one which changes by changing this direction along a singularity, if I subtract these two, then I get something like my one instanton result.
Can I ask a question?
Sure.
So if you take the Borel transform against the positive axis,
Yeah.
do you recover the true value of the integral or not?
That depends, because the true value of the integral is also not well defined, because because it's an integral of a quartic function, and I can integrate it along different contours in the plane.
Integrate like you wrote on this blackboard.
Yes, then you will get the same result. Yes.
Then I will recover the true value of the
Yeah.
integral. Well, then it's a solution of the problem.
It's a solution of a problem, but I mean this problem is very simple, so I'm using techniques that might be a bit too much for this. But you might now say, now let's change the problem and say I have different contours that I can integrate this over. Then I'll find slightly different answers, and these different answers will differ by exactly the non-perturbative contributions that you find here. There's another question.
Sorry,
Yeah.
this one makes me just like ignore it, but somewhere in there, an e to the minus 1 on 16 lambda turned into an e to the 1 on 16
Oh.
lambda positive.
That it could be. Let me check.
E to the positive 1 on 16 lambda looks like I wouldn't call that a small non-perturbative. I wouldn't.
Yeah, there should be a minus here, indeed. Yeah. Or
I think on the previous slide it was still positive. I mean,
and there might be a sign here already.
No, it's correct.
Okay. Either way, I'm not going to chase through my slides to find a minus sign, but it's consistent when you do it correctly. Yeah. I'm sorry about that. Okay, so this is sort of the general lesson. I can take my perturbative series, Borel transform in different ways, and the difference will be an instanton result. And to make this more precise and generalize this to higher instantons, for example, we have to go to the work of Jean École and to this Resurgence. So let me now give you a very quick glimpse of what Resurgence is about. And this will be a very quick glimpse because I would really need a 1-hour seminar or several ones to discuss this. But the upshot of Resurgence is exactly what I just told you. For many systems, perturbation theory around any background contains full information about all other instanton sectors. And to see this, it's useful to introduce a new object called a transseries, which is also a formal power series expansion, but it's a power series expansion in more than one object, which is where all of these objects are themselves function of a single variable. So let's give a simple example here. I here have a power series, n and m are my summation variables, in x, but also in e to the minus 1 over x. So I sort of treat my non-perturbative instanton contribution as a new perturbative parameter. Now it's often useful to use series like this and to treat them as generating functions also of the instanton contribution. So to introduce an extra variable sigma which sort of counts the number of instantons I have. So instead of writing them this way, I will write these functions this way. I will introduce an artificial sigma to the power n. And then to make this not introduce an actual extra variable, I will just impose that C10 equals 1 so that my C10 sort of sits inside this sigma. So I'm not really doing anything extra here. I'm just rewriting my original function in a more convenient way. And often in physics, you can actually construct transseries solutions to a problem. And a canonical example to keep in mind is Painlevé-1. Here's the Painlevé-1 equation, which is a very physical equation. It describes, for example, the free energy of pure two-dimensional gravity. And this equation has a power series solution, but it also more generally has a transseries solution. I will show you what it looks like just to show you that it can be done. And to do that, I will have to do some slight renormalization or definitions. I will divide my u by a factor square root of z, and I will introduce this parameter x, which is a certain power of z. And if you do that, you can indeed find a transseries solution to Painlevé-1, and it looks quite simple. You will find that the instanton action appearing here is this simple number, and you will find ordinary series expansions now around each of these e to the minus na over x. The first one is written here and is very well known, but you can find further ones as well. Now, if you're a string theorist, you might notice that here you have an expansion in x squared, and here you have an expansion in x. This has the following string theoretic interpretation. Two-dimensional gravity is actually a very simple string theory, so it has a string coupling constant, and this string coupling constant actually turns out to be x, but x is the open string coupling constant. And one instanton in string theory is just one d-brane. So this you should think of as an expansion around one d-brane, two d-branes, and so on. Now, if I have no d-branes, then I have a closed string theory. So I will find an expansion in a closed string coupling constant, which is indeed the square of the open string coupling constant. So this is why, indeed, you find an x squared expansion here and an x expansion here. You can actually go further, because this was a one-parameter transseries solution, but Painlevé-1 is a second-order ordinary differential equation. So you might expect to find a two-parameter solution to it, and you can actually do that. You can actually write a double transseries with now a sigma 1 and a sigma 2, where the power of sigma 1 multiplies the original e to the minus na over x, and sigma 2 actually multiplies e to the plus ma over x. So sigma was just a useful parameter that counted the number of instantons. It's a formal parameter. So I have a formal solution in sigma 1, sigma 2, and x. And sigma 1 is the generating variable that generates the generating function.
What's the relation of sigma 1 and sigma 2 to the Painlevé?
So there are the two parameters in Painlevé. Painlevé-1 has a two-parameter family of solutions, and I can choose arbitrary sigma 1, sigma 2, and then find the solution. So in this setting, they're integration constants. Yeah. You might also ask about the physical interpretation, because I just said well, x sort of is a string coupling constant, so x counts the genus. Sigma 1 sort of counts the number of d-branes, And I wish I could tell you what sigma 2 counts, but it's not quite clear. So there's an interesting open question here as to what the physical interpretation of these other objects are. There's some sort of non-perturbative action. It's very tempting to think of them as anti-D branes maybe. But if they were really anti-D branes, then you could say, well, I can take one brane and one anti-brane, put them together, and they would annihilate. So you would then expect that this U11, for example, would equal U00, and it's not. So they're not quite anti-branes, but they're something different. Okay. Now, let me take some asymptotic series, and let me have some direction where its Borel transform has a singularity, so that I can jump across it. Now, I would want to tell you a bit more about resurgence, but because I don't have too much time, I'll actually skip a lot of the technical resurgence details and just tell you something about the results of resurgence. So let me skip a few slides ahead. One more. And tell you a result that follows from all this resurgence framework. And what it does is it does exactly what I told you in the beginning. It tells you something about how an expansion around a no instanton background is related to an expansion around multiple instanton backgrounds. And this is an example that follows for Penlevé 1, for example. So what I have here, the CGs, are the perturbative coefficients in my Penlevé 1 solution. And what I have here on the right-hand side are the coefficients in the k instanton backgrounds of the Penlevé 1 solution. So what this equation really tells me is how to, if I know all of these coefficients, how I can find anything around multi-instanton backgrounds. Let me make this a bit more clear on the following slide. So let's look at this formula. Here I have the perturbative solution of Penlevé 1, the coefficients in that. Here I have a double sum, but for now let's just take the simplest term in that sum. So let's take k equals 1 and h equals 0. Then all I have here is basically a gamma of g divided by some numbers. So what this tells me is that the CG grow as g factorial. Well, that's something we saw in the beginning as well. We have an asymptotic series where the coefficients grow like g factorial. There's a prefactor there that's not very important for now, but what's more important is if I now start looking at the following terms in this H series, then I can get gamma of g minus 1 first, then g minus 2, g minus 3, so I get lower gamma functions. So I get 1 over g corrections. So the large order behavior of this goes like g factorial, but the 1 over g corrections to that are actually determined by this C110. So by the simplest coefficient around one instanton. So from 1 over g corrections to my large order behavior of my perturbative series, I find the first coefficients around the instanton. Then from the second term, I get gamma of g minus 2. So I get 1 over g squared corrections, which are given by the second term in the one instanton correction. And in this way, I can get the full one instanton solution just from the perturbative solution. And I can go further and find the 2 instanton solution, the 3 instanton solution, and so on. So what these resurgence techniques that unfortunately I have to leave mysterious do for you is really tell you how you can get instanton solutions from purely perturbative data. Instanton corrections, solutions around instanton backgrounds. Yes. Okay, so very briefly let me tell you how people have applied this in recent models. And these applications all go in the following directions: minimal string theories, matrix models, and topological strings. And topological strings is sort of the holy grail of all of this, because this is a theory where we don't really know what the non-perturbative definition of the theory is. So this gives us tools to learn about non-perturbative properties of topological strings, even though we might not know the full solution. Well, you have to... yeah, if I could quantize gravity, I would, but for me, I would be very happy if I can give a non-perturbative definition of topological string. So one thing you can do is look at minimal string theories, and basically we've already done that, because minimal string theories, the canonical example is pure worldsheet gravity, which is Penlevé 1. The other ones are other differential equations, but you can apply all of this to that. And we did this in a paper that appeared last year. Indeed, there you can construct two-parameter transseries. I already said that you find closed strings in the NN sectors, open strings in the other sectors, so you indeed find D-brane solutions. And you also find stuff that's already known. So you find that indeed you find the correct D-brain action, for example. There's still something unclear, but that's an interesting open problem to work on. And I will skip some plots, but just to show you how well this works, if I take this formula in PenLevé 1 and I want to calculate, for example, C30 using coefficients here, then you can indeed see that if you sum up to 6 instantons, 1, 2, 3, 4, 5, 6 instantons, you get to 60 decimals of precision of this coefficient. So this indeed is a way to sum up lots of instantons and find really precise results. You can do the same for matrix models. That was also done in this paper, and there's another paper to appear soon on this. And this already gets a bit more interesting, since matrix models are dual to topological strings. So here you find indeed information about topological string theory by the Dijkgraaf-Waffe conjecture. But it's still sort of matrix models that are related to models we know. So finally, what we're working on now is to do this for topological strings that we don't know a non-perturbative definition on yet. And how do we do that? Well, you need, again, an equation that you can plug your transseries into. And one interesting equation to do that is the holomorphic anomaly equation of BCOV. And this is a project that we're working on now and that I'm very excited about. Because what you can do here is very similar to what's known as direct integration. There's this technique that was started by Clem and collaborators and then applied by many others of calculating topological string partition functions by just looking at boundary conditions on moduli space and using this holomorphic anomaly equation. And you can do exactly the same in the non-perturbative sectors. So you can find a full transseries solution. So you find a complete non-perturbative topological string partition function. The instanton actions you find are indeed proportional to periods, like they are in cases that are known. And of course, the main open question now is how to physically interpret all of this. That's something I cannot tell you too much about yet. Hopefully in the future I can. But for now, Resurgence gives us a very nice mathematical handle on this non-perturbative topological string theory. And hopefully that's a start to get a better physical handle as well. So since I'm already over time, let's stop there.
We don't have time for questions.